In section 4.3, we're looking at an alternate method of solving a system of equations. The big downfall of solving a system of equations with substitution is what happens if we're in a scenario where, like this one right here, where with the substitution method, I told you that you need to look for a variable that has either a 1 or a -1 as its coefficient, because that means when you solve for that variable, you're not going to end up with fractions. If you have a system of equations that looks like this, all of the coefficients have something other than a 1 for all the variables have something other than 1 for their coefficient. So that means when I solve, no matter which variable I solve for, I'm going to end up with fractions floating around everywhere. So this is where the elimination method comes in. The elimination method gives us an alternate method of solving these. And basically how this works is it recognizes if we have two equations and we're assuming both of those equations are true, well, in general, when we're solving a system, or when we're solving an equation, if I had something like x plus 4 equals 6, in order to solve this, what I do is I add the same value to both sides of the equation. I would add a -4 to both sides. And over here it would cancel out. Over here I'd get x equals 2. If I'm assuming both of these are equations, that means both of these equations are true, that means x plus 3, or x plus y, is the same as 13. So what I'm going to do is I'm going to take and add x plus y to this side of this equation, and add 13 to that side of this equation. In effect, what that means is I'm going to be adding these vertically. So I'm going to take the x plus the 2x to get 3x. I'm going to take the y and the opposite of y, and it looks like you can see those actually cancel out. Get plus 0y. And over on the other side of the equation, 13 and a -7 gives me 6. So the y's dropped out, and I end up with 3x equals 6. Well, actually, this is kind of ideal, because before, with the substitution method, the whole point of making that substitution was to make one of the variables go away. If I solve for y and then substitute in y, then the y's end up going away, and I solved for x. In this instance, I added these two equations together, and the y's went away. I end up with just an equation that has x's in it. So that means I can solve this equation, and that'll tell me a value of x. Well, I get x equals 2. Turns out this is the x-coordinate of our solution, just like before. And to finish this up, I'm going to follow the exact same method I followed with the substitution method. I have the x-coordinate. I need to now find the y-coordinate. And to find the y-coordinate, I can plug this value, this x-coordinate, into either of these equations. It looks like this first equation is the easier one to plug into, because there's not any multiplication or anything like that going on. So that's what I'm going to do. That's where I'm going to plug it in. So now to find y, I'm going to plug into the first equation. So I get 2, well, let me recap the equation here. The first equation is x plus y equals 13. When I plug in x equals 2, I get 2 plus y equals 13, and thus y equals 11. This gives me in total the point 2, 11. It's always a good habit to be in, it's a good idea to be in the habit of checking your work here. So let's verify that this point satisfies both of these equations. So first off, 2 plus 11. You'll notice I'm just plugging in this. X is 2, y is 11, so 2 plus 11. I press enter and I get 13 for the first equation. For the second equation, 2 times 2 minus 11. I expect this to be -7, and you can see it is. So this point does satisfy both of those equations.